Hello everybody, welcome to the first lecture of MATLAB optimization. Today we are going to solve any linear programming optimization problem using MATLAB linprog 1. So in order to solve a optimization problem using linear programming, we have to make sure that all the equations are linear equation. So here are the example of linear equation. So note that in this equation the value of the power of each variable is 1. The power of x1 is 1, the power of x2 is also 1, the power of x3 is also 1. This is the most important step. So we have to make sure that all the variables have same power. Also, there is no product of two variables. So x1 is not multiplying with x2 and so on. Similarly, there is no dividing between two variables. So these two equations are the example of linear equation. Now we will see some of the equations which are not linear. So here this equation is not a linear equation because two variables x1 and x2 are multiplying with each other. Similarly, this equation is not a linear equation because there are higher powers. So the power of x is 6 and the power of y is 4 and so on. And this equation is not a linear equation because two variables x and y are getting divided by each other. Similarly, if there is some sine of variable or cosine of variable or log of x or log of y, so that would also be a non-linear equation. So in order for equations to be a linear equation, it has to be in this format so that it can be written in the matrix format. So let's take an example of a linear programming optimization and then we will solve it in the MATLAB. So here is our objective function. Minimize minus 6x1, minus 18x2 and minus 72x3. So we have to minimize this objective function. We have to minimize this equation. Note there are three variables x1, x2 and x3. So now there are three constraints. So this objective function has three constraints. So these three constraints must be satisfied. So these three constraints are inequality constraints. So this is also a linear equation and it has the sign of non-equality, less than or equal to. So our first constraint is 7x1 plus 4x2 plus 2x3 should be less than or equal to 16. And this should be the format of a non-equality constraint. So in the second constraint, the sign is inverse. This is a greater than or equal to sign. We have to convert this greater than or equal to sign into less than or equal to sign. So how we can do that? We can just multiply this whole second constraint with negative 1. So when we will multiply this whole constraint with negative 1, it will become minus 4x1 minus 11x2 minus 4x3 less than or equal to minus 72. Now this sign has been changed from greater than or equal to less than or equal to. So this is the format, this is the format, and the third constraint is this one. So these three constraints are inequality constraints or non-equality constraints. Now this constraint, this is an equality constraint, it contains the sign of equal. So notice that there is no x1, so we will take the coefficient of x1 as 0 and then there is the coefficient of x2 is minus 11 and coefficient of x3 is plus 20, and this is the right hand side of the equation. Now this optimization problem is subjected to upper bounds and lower bounds. So each variable has a lower bound limit and upper bound limit. So x1 has the lower bound of 0 and upper bound of 500, which means the minimum value of x1 can have is 0 and the maximum value that the x1 can be is 500. Similarly, the minimum value of x2 should be 10 and maximum value should be 25. Similarly, the lower bound of x3 should be 0 and upper bound of x3 should be 16. We will also define that in our MATLAB code. Now let's start with the coding process. So here is the MATLAB interface. We have a command window, we have a workspace, and we have our directory. So we will use the command window only to show us the output result. So we will create a new script, and in this script we will do all the coding. So first I'm going to write this command clc clear and close, and then I'm going to save this script. So the name of this script is linear programming example. So we will first define our objective function, which is f equals to. So here is our objective function. So we have to write this in the matrix form, in the coefficient form. So its coefficient is -6, -18 and -72. So we will write it -6, -18 and -72. So note that I have added some spaces. Space means a column separator. So now when we are going to run this code, we have in the command window f has 3 coefficients. So -6 is the coefficient of x1, -18 is the coefficient of x2, and -72 is the coefficient of x3. Note these 3 values are in separate columns. So this is in the column 1. So we will store the values of x1 in column 1, we will store the value of x2 in column 2, and we will store the value of x3 in column 3. So space basically is a column separator. It means we are writing the next value in the next column. So now we will define the second constraint. So we will define our inequality constraints. So let's say a equals. So this is our first inequality constraint. We will write the coefficient of x1, which is 7, x2 4, and x3 is 2, 7, 4, 2. So we will write it here, 7, 4, and 2. Then we will write another constraint, our second constraint. For that we will add a semicolon, which means a row separator, which means we want to write the next values in the separate rows in the next row. So our second constraint is the converted second constraint, which has the coefficients -4, -11 and -4. So we will write that -4, -11 and -4. Now we will write our third constraint, which is 2, 4 and 19. So 2, 4 and 19. So this is our A matrix. Now when I'm going to run this code, it will show me the matrix A. So matrix A inequality is 7, 4, 2 in the first row, and then we have added a semicolon, which means a row separator. So in the next row the value of -4, -11 and -4, and then I have added another semicolon, which means another row, a third row, which has the coefficients 2, 4 and 19. So now this is our inequality matrix A. So now we need to add B inequality, which is the right hand side matrix. So in this case the right hand side vector would be 60, 72, 60, -72 and 100. So, and these should all be in separate rows, so we will add a semicolon after each value. So the first value is 60 -72, 60 semicolon -72 semicolon 100. So this is a matrix format. So when we will run this code, we have our B inequality 60 minus 72 and 100, and this is a row matrix, so each value is in a different row. So now we will define our A equality matrix EQ, which is going to be this matrix. Note the coefficient of x1 here is 0, so we will write 0, and then coefficient of x2 is here is minus 11, and the coefficient of x3 here is 20. So we will write that 0 minus 11 and 20. Similarly, we will write B EQ, which is equal to minus 105. So B equality is equal to minus 105. Now we will define our lower bound and upper bound for each variable. Since we have three variables, so the lower bound of x1 equals 0, lower bound of x2 equals 10, lower bound of x3 equals 0. So we will write that 0 and 0. So all the lower bounds we will define in the LB matrix, and now we will define the UB matrix, which is upper bound of each variable. Upper bound of x1 is 500, upper bound of x2 is 25, and upper bound of x3 is 60. So 500, 25, 60. 500 space 25 space 60. So we have defined all the required parameters. We have defined our objective function, we have defined our inequality constants, we have defined our equality constants, and now we have defined our lower bounds and upper bounds. Now we will define the linprog function of MATLAB. So let's say we need the values of x. So x equals, so this is the optimal solution. When you will use the MATLAB linprog function, it will store these all the values of x, y, and z, x1, x2, and x3 in this matrix. So now we are defining linprog, and we are starting a parenthesis. So after starting this linprog, prog, okay. So now when we will start this, it will ask us the whole command. So it's asking us to input f, a, b, a equality, b equality, lb, and ub values. So we will define here. So our objective function is f. We will put f, comma. Our inequality constant matrix is a inequality. So we will write a uneq, because this is our inequality matrix. Now we will define b uneq, which is our right hand side matrix of inequality. Make sure that this is underscore and u is a small, and this is uneq. Okay. Now we have added a comma, and we will copy its name and we will paste it here, because we have to write equality matrix, a equality matrix. Now we will define b equality matrix. So we will copy its name from here and we will paste it over here, and we will define the matrix LB, lower bounds of each variable, and UB, upper bound of each variable, and then we will close the parenthesis. Now when we will run this code, so here we can see that the optimal solution has been found, and the value of x is this one, 0, 13.823, 2.3529. So this is our optimal solution. So MATLAB is telling us that these values are, so this is the value of x1, this is the value of x2, and this is the value of x3, that these values of x1 and x2 and x3 satisfy all our constraints, both inequality constraint as well as equality constraint, and they also give us the minimum value of our objective function. So what if we want to find what is the minimum value of objective function? So what we will do, we will just multiply f with x. F multiply x. So the answer is minus 418. So when you will put the values of x1, x2, and x3 that you obtained above over here in your objective function equation, which was this equation. So when you will put it into this equation, so it will give you the minimum value of your objective function, which is minus 418.2353. So now there is another way to obtain this value. So we can put up open bracket and we can write here is f wall. So when you will, so it will give you now two results. X would be the optimal solution, which would be these values, and the value of f wall would be the objective function value at that optimal solution, which would be minus 418.2353. So now when we will run this script, we will get these two values. So this is our optimal solution, the value of x1, x2 and x3, and this is our objective function value at these optimal solution, at this optimal solution, minus 418.2353. So now another thing we can add around here, another output this linprog function gives is exit flag. So when we run this code, now you can see that the value of exit flag equals 1. That means that the linear programming has found a solution. So you can see it says optimal solution found. When the optimal solution will be found, the value of exit flag will become 1. So if somehow the linear programming, this linprog function does not found any solution, or the solution does not exist, in that case the value of objective function will be other than 1. It will be minus 1, minus 2, it could be anything else. It won't be 1. So let's change this value b equality to minus 170. So when you will run this code, you will see an error. So it's not an error, it's basically MATLAB is telling you that this linprog function has stopped because no point satisfy the constraints. So that means there is no solution. So if there is no solution, the value of x would be a phi matrix, the value of f wall would also be a phi matrix, and the exit flag is equal to minus 2. It's not equal to 1. So which tells us that the linprog command was unable to find any solution. So this is pretty much it. So now what if we want to find only the maximum value of our objective function instead of minimum value? So in that case, what we will do, so the optimal solution, so we want to find the maximum value, and the optimal solution should also satisfy all these constraints, non-equality constraints as well as equality constraints. So in that case, we can just multiply our objective function equation with -1. So we just need to change the Joe's coefficient. So we just need to multiply this objective function equation with -1, the whole equation with -1. So let's go and implement this in MATLAB. So here we have our MATLAB code, and we can just multiply this value of objective function, which stores the coefficient of objective function, with -1. So all the other things will remain same. So now we can just go ahead and run the code, and now let's see in that case. So here is our optimal solution found. So the value of x1 should be this, value of x2 should be this, and value of x3 should be this. When you put these values into your objective function, the value of objective function that you will obtain will be maximum in that case. But that value will not be 198, instead it will be -198. So the maximum value that the objective function can have is -198. Since we multiplied this objective function value with -1, so that's why the sign is reversed over here. So you just need to change the sign of f wall, and that's it. So the maximum value that our function can have is -198, and the minimum value that our objective function can have is -418. That's it. If you like my video, please subscribe my channel. Also, I'm a professional engineer and a freelancer, and it's been more than 5 years since I've been doing freelancing projects of MATLAB, Excel VBA and Python. So if you want to hire me to help you in your project or provide online tutoring services, contact me here on my WhatsApp or through my Fiverr account.